Today, Charlotte obtained her bachelor and actually 2 masters, not just in chemistry and catalysis, but also in business management in Utrecht. And after that, she started her PhD in the group of Bert Weckhuizen. Her PhD was on the conversion of CO2 to other useful materials, and she carried out the last stage, as I understood from her PhD, in Israel with a prestigious fellowship she obtained, and was then at the Weizmann Institute for Science with Dr. Aaron and Professor Neumann. Got then an award as Outstanding Female Scientist in 2019, and also an early career achievement from Intel Israel, and a Nielsen Stenson Fellowship as well. So, well, a lot of great honors already when she got her PhD in 2020, and then after a short stay as a postdoc, if I'm well, you started your own group in Israel at the Technion group, of course, focusing on catalysis. And since you had a very interesting review paper recently together with your former PhD advisor Bert Weckhuizen, we thought, oh, it might be a good idea to invite Charlotte and to ask her to give a presentation on this idea of how we should look at the active site in a catalyst. So Charlotte, we're really eager to hear your talk, and the floor is yours.
Thank you so much for the kind introduction, and I'll have to excuse myself for my absence 2 weeks ago. I just came down with Corona the night before, so if you hear me coughing, there's some after effects. I will start to share my screen. Okay, and everybody sees that, I hope.
Yes.
Perfect. All right. So it's exciting for me to give this talk for you guys in Delft. It's the first time after I left for Israel a couple of years ago that I will be presenting in the Netherlands, even though it's virtually. And I think indeed that the title of my talk speaks for itself. I'm going to be talking about the concept of the active site in catalysis, specifically heterogeneous catalysis. And it's a concept I'm sure that many of you are very familiar with. Catalysis, of course, is at the basis of all things that we make, synthesize, optimize, man-made. Most things that we do in this way for our fuels, materials, food even, and it's going to play a huge role, of course, also in the way that we tackle the energy crisis and the global warming problem, etc. We all know this. Heterogeneous catalysis is the most applied, the most applied form of catalysis in industry, of course, where the reactants and the products are in a different phase than the catalyst itself. And at the basis of all of this lies this elusive active site where the magic happens, quite literally, I think. And this is an abstract representation of what we know happens at the active site. We talk in catalysis about lowering the activation energy, increasing the kinetics, not touching the thermodynamics. The enthalpy of the reaction remains unchanged. And that happens by optimally binding. We know from Sabatier principles, the volcano plots, optimally binding reactants and products, not too strong, not too weak, this Goldilocks principle. And from Pauling, also already a century ago, who mainly studied enzymes as catalysts, we know that there should be optimal stabilization of the transition state. So Pauling's transition state theory he developed by studying enzymes, and enzymes, of course, have this very nicely defined, very well-defined active site, actually billions of years of evolution, well-defined active site with a couple of metal atoms, single atoms often at the heart of this active site, surrounded by this huge body of protein, right? And we know now that this body of protein is actually imperative to, for example, guide the reactant to the heart of this active site, and even sometimes changes its shape to optimally also facilitate the transition state. And this model thing, it's not a model thing, of course, but taking this as a model for a catalyst, it's quite easy to come up with something that quantifies the activity. right? We can say how many molecules are turned over per enzyme, which is the turnover number. Molecules turned over by an enzyme in a given time unit per second, for example. And what we then did when we were using these concepts, translating them to heterogeneous catalysis, is we took analogs of things like this, like the turnover number, like the turnover frequency, the amount of molecules converted per active surface area. But there already comes the crux. There already comes the interesting part, because what is actually an active surface area? How do we define in a heterogeneous catalyst what is active and what is not? That's what I want to talk about today by use of operando spectroscopy, studying reactions under operating conditions, and then the strictest definition also quantifying the products of the reaction while they're at work. And why we need to do this is because heterogeneous catalysts, as I said, are extremely complex along multiple scales, along multiple dimensions. Very importantly, the length scale, for example, at the angstrom scale, where we have the seemingly simple cleavage of a nitrogen over any bond. Nanometer scale, where we have nanoparticles on a support, which make up a very important class of catalysts. Centimeter scale, we have extradates, where at the inside of the extradate, as much as we try due to mass transfer limitations, we can still have different catalysis on the inside of this centimeter scale extradate than on the outside, or wherever in its positioning. We have the meter scales, of course, the reactors that we have in industry, and reactions can, again, be very different. Conditions can be very different at the top of the reactor versus any other place at the bottom. And then finally, we have at the end of this length scale, the kilometers of chemical industry that we rely on for everything we see around us, almost. And then another very important time scale, another very important dimension is the time scale, where we have reactants, which exist around somewhere between the femtosecond and nanosecond time scale. Surfaces can reconstruct at the second scale. Some catalysts need hours or even weeks of activation time, like Fischer-Tropsch catalyst, for example, slowly filling the pores with hydrocarbons until an equilibrium state is reached. We have catalyst deactivation, which can occur, all kinds of phase transformations that can occur on the second time scale. If you look at a fluid catalytic cracking catalyst, for example, it only reacts in the riser for a few seconds with oil until it's deactivated, regenerated, etc. And the whole circle begins again. And catalysts can also deactivate on the year scale. For example, hydrogenation catalysts typically deactivate there. So we have such a complex picture of different catalysts. We can classify different types of activity in heterogeneous catalysts. We can look at, for example, Brunstad and Lewis acid sites. Typically there for solid acids, covalent bonds formed, broken. Cracking of hydrocarbons is a good example of a Brunstad acid site catalyst. Olefin polymerization for Lewis acidity. We have basic sites, slightly less known or applied, I would argue, also covalent. Lebedev process is an example. Redox sites, these are more like, I would argue, more like enzymes, where you often have atomically dispersed metal atoms. The bonds there involved are ionic, can also be covalent. Selective catalytic reduction of NOxes is a great example there. And then metal sites, which I'll actually go into the most in this entire presentation, where, of course, there are also metals involved in these redox sites, but we can make this distinction basically on the basis of metal behavior, of band structure formation versus atomic behavior. But of course, it's sort of a metal covalent hybrid bond that we're talking about. And typical examples are CO oxidation, dehydrogenation catalyst, hydrogenation catalyst, Fischer-Tropsch synthesis, CO2 hydrogenation. I would argue that this supported metal classification is the most versatile. That's maybe because I've been studying them the most in my short career. So typical examples of active sites, typical examples of heterogeneous catalysts. For the Brunstad acid site, I already mentioned a little bit before. Cracking of hydrocarbons, fluid catalytic cracking, for example, is often a sort of textbook example of Brunstad acid site catalysis. So let's examine what happens in that catalyst. We have a Brunstad acid site created by the substitution of an aluminum in a silica framework. And the acidity of that is heavily reliant on the confinement of the cages or pores around it, right? The acidity of amorphous silica or amorphous silica aluma, it's much less than the acidity of a confined OH site. But that's not the only thing that FCC catalyst has. We also have clays, binders, Lewis acidity. Even it's said that the cracking of hydrocarbons, can actually only occur if it first encounters a Lewis acid site. So you definitely need the cooperation of those two different sites for optimal activity in an industrial setting. And then we have on that same catalyst, often metal impurities coming from the oil that it catalyzes, and those metal impurities can hydrogenate, can have all kinds of unwanted side reaction formation. So this typical example, this textbook example of what should be a pretty simple, well-defined active site, you can see that in reality, if you're studying catalysts as close as you can to working conditions, it's so much more complex. Same can hold for olefin polymerization catalysts, Lewis acid sites. You can see that in the polydispersity factor. It's always not one, right? There's always some homogeneity in how polymers are formed. Redox site is a great example. There's still a lot of discussion, even though there's some great work, also great operander spectroscopy work on trying to understand the nuclearity of a copper site in a zeolite. There's still a lot of discussion on whether it's mono, di, or even tri site, dependent on where the alumina is, the T site is located within a pore, within a cage. And then for a metal site, for example, CO oxidation, platinum on a support, we can already, just by the geometry of the nanoparticle, define that not all of the atoms are equal, right? We have terrace sites, flat sites, we have stepped sites. We can definitely have oxygen there. The oxygen can be on the surface. The oxygen can be inside the nanoparticle. We can have platinum support interface sites, because these are suggested to be extremely important. Where also there's a role of the support in the entire picture of the catalytic cascade, let's say. So already these textbook examples of catalysts and of catalytic sites are, you can see they're extremely complex and ambiguous in all cases. They are extremely ambiguous. So what we do is, as scientists, of course, we try to simplify. We try to make models, and this is what we already did about a century ago. And there are two main schools of thought that a lot of our basic understanding of catalysts come from. We would argue. The first is Langmuir. Langmuir made a lot of his models, made a lot of his approximations, I should say, based on a few oversimplifying assumptions. They were very valid to deduce some very valuable kinetic models. He looked at active sites as polychrocies, and along with some other important assumptions, like, for example, no lateral interactions between intermediates absorbed on the surface. He was able, and people who followed this train of thought were able in the next decades to really develop some great kinetic descriptions of catalysts. So apparently there was some validity to these assumptions. It's also the basis for a very important subfield of catalytic studies, which is surface science. Not just catalysis, of course, but mainly, where we study single crystal facets, model surfaces under often ultra high vacuum conditions. Now we're moving closer to relevant conditions also with surface science studies, but typically speaking, 80s, 90s, ultra high vacuum, 10 to the power -12, and studying really atomic events, molecular events happening on these model surfaces. I think we can all agree, and specifically in the last 2 decades, we've begun to see more and more that this oversimplification also often really does not hold up in terms of reaction mechanisms, in terms of the way that surfaces behave. We can see cluster formation at slightly higher temperatures of single crystal facets, which has been shown very recently. So there's this other school of thought made by Taylor, who actually is from the same time period. And he viewed catalysts as or catalytic sites as oligarchies. He would say certain sites have all the power, are the most active, and other ones are not active at all. It's either blue, green or red. And this led to the Taylor ratio, which is always lower than 1, meaning there's always some surface, some part of the surface that is not active. This is really the basis of the school of thought, or the basis of this other direction of studying catalysts, which is the operando way of thinking. And this is a methodology that I described before, studying catalysts under working conditions while quantifying the products, that got a name really about the last 2 decades, and is leading also to more and more developments in transient techniques, single molecule and single atom methods, really over the last couple of years. And I want to take this last school of thought, which I think is much closer to reality, not in any way saying that the Langmuir school of thought is not also valuable to approach things, as you'll see, because I'm borrowing some things from there. But trying to analyze that statement, let's say, the red and the green. Should we look at nanoparticles as having active sites or inactive sites, or is there even some more nuance in there? And to do that, and to also try to dissect sort of the different physical principles that actually contribute to active site activity, I want to discuss structure sensitivity, which was a very important part of the studies that I've been doing over the last couple of years. So structure sensitivity, structure insensitivity, means as much as not all atoms of a catalytic nanoparticle having the same activity. And that is because different nanoparticles have, aside from having more or less bulk, when you change the nanoparticle size, they also have different types of sites that are available. Right? You have, on a 1.2 nanometer particle, for example, most of the surface that is exposed is this pink or orangey, highly undercoordinated surfaces, step edge sites, B5 sites, etc. And for a 5.5 nanometer particle, you can see most of it is bulk, but of the surface that is exposed, most of it is highly coordinated. And because molecules, atoms, interact differently with these different types of sites, depending on their coordination, we can see different, empirically, we can derive different trends with how reactions, how the activity, the surface normalized activity of reactions correlates to particle size. And this, of course, is an interesting phenomenon, because I already said that I already said a couple of slides ago that the turnover frequency, I had some critique there, because how do you actually define the active site of the active surface area, sorry, of a supported metal catalyst, when you know that there might be different sites with different activity? Well, by taking the surface normalized activity and looking at activity trends over different nanoparticle sizes, basically it's a way to look at whether that premise is true or not, right? If the activity, the surface normalized activity changes for different nanoparticle sizes, it means that not all atoms have the same activity. So basically you're invalidating the turnover frequency while you're using it. But nevertheless, this empirically led to 3 different classes of structure sensitivity. First, sigma type, where the activity of a nanoparticle, surface normalized activity of a catalyst, increases exponentially with a smaller catalyst particle size. That's because sigma bonds are preferentially cleaved over highly undercoordinated sites. We have class 2, pi type structure sensitivity. Pi bonds, or reactions where the rate determining step is the cleavage or formation of a pi bond, need a certain degree of coordination, need, for example, B5 sites. So you see that there's often an optimum, sometimes there's a hockey stick type behavior where it flattens off at a certain range. But in any case, it decreases for the surface normalized activity decreases for smaller nanoparticle sizes. And then there's this third class of structure insensitivity, which is empirically observed, but we'll get into that also a little bit later. But we basically see that there is surface heterogeneity by knowing that there is, or by observing that there is structure sensitivity. And let's dive into that a little bit more in detail. So, excuse me. Here, let's take a look at CO2 hydrogenation over nickel. CO2 hydrogenation over nickel, specifically supported on silica nanoparticles, really almost only forms methane, has about 100% selectivity towards methane. So it's a nice and simple reaction to try to study these fundamental principles. And even though it's quite simple, we can still see that there are different pathways, of course, that can be taken to form methane, to form that single product, carbon monoxide pathway, formate pathway, carboxylate pathway. And what we did here was we took these single crystal facets, right? This Langmuir approach, basically calculated the absorption energies on all of these. From there, the activation energy barriers, etc. And we used these facets, the information that we obtained from them, superimposed to build a nanoparticle, and thereby rationalize some of the things that we wanted to rationalize. So just by looking at the chemosorption energy of CO2 on those nickel facets, we could already see that there was a big degree of structure sensitivity just in the very first step of that catalytic reaction. And this shows how much actually a nanoparticle is sensitive to the different types of steps that are going on. And even it's also a very good display of how heterogeneous this super simplified way of looking at a nanoparticle really is, because just this one facet we can see that there are 7 different types of absorption sites, let alone on all of these different facets that we took, which are just a small fraction of the different types of sites that we would really think to observe on a nanoparticle under working conditions. So already the very first step is structure sensitive. So let's now take those chemosorption energies and calculate the activation energy barriers for all of the different reaction intermediates on all of these different facets, which we did. You end up with numbers like this. We take those activation energy barriers forward, backward, build a microkinetic model, and then I want to take that information and do a thought experiment with you. Let's say that we have nanoparticles of different sizes. So we build them via Wolf constructions, which of course, caveat, are nowhere close to what nanoparticles would look like under higher temperatures than 0 Kelvin. But bear with me for just this thought experiment. Let's say that we have a 2 nanometer particle. We can see that the ratio of terrace facets, or ratio of different facets, is different for this 2 and the 16 nanometer particle. It's displayed here. So 211 stepped facet, purple, much more in a small nanometer. Again, a small nanoparticle, much less in a 16 nanometer particle. Then we took the rates for methane formation on the different facets and used those along with the ratio of facets that were exposed to come up with the overall rate of methane formation, and then deduce from that different fraction of so the relative contribution to the rate of the different facets that were exposed, if that makes any sense. Basically, what we did was we tried to see if we calculate the methane rate on those different nanoparticle sizes, by the way, which goes up with smaller nanoparticle size for now. How much of that rate now comes from those different facets? So for the small one, we see that most of it comes from 211. So I would say for a 2 nanometer nickel nanoparticle, I would say that the active site, or the most active site maybe, is this 211 nickel facet is the active site. Then we move to a 60 nanometer nickel nanoparticle for the exact same reaction. We see that there most of the activity comes from a 111 surface, actually not this 211 surface. For the same metal, we have different active sites, and even the activity of the active site is supplemented by different facets as well. And it could very well be that these different facets are very important in a given reaction step leading up to the rate determining step. So I would argue that this picture of defining an active site on metal nanoparticles is way too it's a pipe dream, basically. It's something that's inaccurate almost to do, even on this very, very simplified thought experiment that we did. So in reality, already by just looking at theory, we can say that this red and green should actually be, if we take the reaction coordinate dependence into account, should actually look a little bit more like this. First step, certain sites might be more active and others might be less active. And for a different point in the reaction coordinate diagram, others might be much more active. And the ensemble picture of those two together is what you should take into account if you only take into account the reaction coordinate dependence. And we'll build up to even more complicated picture while we're going through the presentation. So again, I promised you operando spectroscopy. Here we're going to go into some experiments. As I said, we have a structure sensitive reaction, CO2 hydrogenation. The surface normalized activity changes with catalyst particle size, basically showing that we shouldn't use turnover frequency as a way to describe the active surface, but it's a great way to show that there's this difference. If we study those different nanoparticle sizes, so we synthesized nickel nanoparticle sizes on silica supports ranging from 1 to 6 nanometers in this very interesting size range where we change most of the fractions of the surface sites exposed, and we studied them with operando infrared spectroscopy. So CO2 conversion over these nickel nanoparticles of different sizes, and then measuring infrared spectra the entire time. We can see that the infrared spectra in this region, which is the region where you would expect CO vibrations to occur, you can see that they're completely different for a small, medium, and a large catalyst particle size. For the small catalyst particle size, we can see something here, which is gassy CO, which we can't see here or here. And I know that it's slightly askew the way of looking at it, but in this case, you'll have to trust me that we didn't see any gaseous CO for the middle and the larger catalyst particle size. What we did see is different absorbed CO peaks. This region we saw for the for the medium catalyst particle size, we saw a lot of linearly absorbed CO, whereas for the larger catalyst particle size, we saw a lot of bridge CO, absorbed CO. And those differ in their bond strength of metal carbon. The linearly absorbed CO has relatively a weaker metal carbon bond, and the bridge CO, which is bound to two nickel atoms, CO is bound to 2 nickel atoms, it has a stronger metal carbon bond. So there's a CO absorption strength dependence, the Sabatier relationship basically for CO for CO2 hydrogenation over nickel catalysts. We see gaseous CO for the smallest, linearly absorbed CO for the medium, and we see this really strongly absorbed CO for the larger catalyst particle size. So we can see that there are different sites apparently on these different nanoparticle sizes. And how do we now explain that effect? How do we explain, fundamentally speaking, dissecting the principles that contribute to this structure sensitivity? So here we take our different catalyst particle sizes and we took them to a synchrotron, the SLS, the Swiss light source. We measured quick X-ray absorption spectroscopy, so an X-ray absorption spectrum per 100 milliseconds, very high time resolution. And then we pulsed CO2 and hydrogen, CO2 and hydrogen, CO2 and hydrogen. And we saw how the different catalyst sizes, nanoparticle sizes, how they responded to those different pulses. And two main things could be deduced from that. One is that the smaller the nanoparticle, the more difficult it is to re-reduce the nanoparticle to its original state, and also the more oxidized it becomes upon the introduction of CO2. It could mean that there are more oxidized or charged species that are more difficult to remove from smaller nanoparticle sizes. And we also saw this really interesting phenomenon occurring, which was during one pulse, we saw two different speeds of things happening, two different kinetic regimes of metallic nickel dependence. So sorry, here on the y-axis is metallic nickel, which basically you can see as an X-ray absorption spectrum measured every 100 milliseconds, and then that spectrum you can take By fitting with two known references, you can take the degree of metallic versus versus nickel oxide state, and we plotted those with time in a very oversimplified explanation of what we actually did, but I don't have that much time to go into it. So this is the speed of changes in oxidation state, and again, we can see two different speeds, meaning that there are, geometrically speaking, two different things that are occurring. Once one thing is up, once one thing is used up, the other thing starts to occur. So actually, how we can explain this structure sensitivity effect is by a geometric effect, right? Their availability of at least two different sites, as we can see here, and an electronic effect. We can see that the smaller nanoparticles are more difficult to re-reduce. They're more easily oxidized. So these two physical principles can be pulled apart from one another and explain activity in these metal catalysts. And this is not something this was something that was also theorized, right? Norskov had a very nice paper in 2008 where he showed that this geometric effect and electronic effect, you can separate them. They're correlated, obviously, but you can separate them based on Blunstead-Evans-Boulogne relationships, different metals along the electronic effect line, alpha, and different facets on the geometric effect line, beta. So that's very cool. We were able to see that experimentally, this electronic and this geometric effect, really two different things that determine catalytic activity. And he made a very interesting comment also in his paper, and it's something that I explained at the beginning of the talk, is that the absolute absence of any structural effect, both geometrical and electronic, is unexpected. No examples can be found. If you remember, when I was explaining structure sensitivity, we had two classes of structure sensitivity, and we had this class of structure insensitivity, which was empirically observed. Basically, if we explain our catalytic activity by electronic and geometric effects, and we know that nanoparticles have different sites, whichever way you can put it, it's very strange that we see structure insensitive reactions if we know that our catalytic activity is at least caused by these electronic and geometric effects. So we took our catalyst nanoparticles, we actually synthesized a whole bunch more nanoparticle sizes, compared the CO2 hydrogenation activity, sorry, surface normalized activity over these nickel nanoparticle sizes against ethene hydrogenation, which is a typical structure insensitive reaction. This is seen as a structure insensitive reaction, the recombination of an absorbed alkyl with hydrogen. And we see that there's, we see a little bit of a dependence there, but we see that it's structure insensitive reaction. And also in literature, this is observed. Strange. We look at FTIR spectroscopy and we try to examine the different nanoparticle sizes again and the different reaction intermediates on the surface. Different representation, same results as I showed a few slides ago for CO2 hydrogenation. We see different reaction intermediates on the surface of the different nanoparticle sizes. And for ethene hydrogenation, not surprisingly, you see that we see no difference in the reaction intermediates absorbed on the surface. But once we took these samples, we took these catalysts again to the synchrotron, and we looked at what happened to the X-ray absorption spectroscopy, to the X-ray absorption spectra. There we saw something that was completely unexpected. For the ethene hydrogenation, which is a structure insensitive reaction where we saw all the same reaction intermediates on the surface with IR spectroscopy, we see that the catalyst restructures enormously. And in the two regions of X-ray absorption spectroscopy that you can identify, which is the Zanes region, which is predominantly changed by electronic effects, or the XAFS region, which is more descriptive of geometric effects, localized electronic geometry. you can see that the geometric region, this x-axis, like there's really restructuring going on with this ethene hydrogenation catalyst for all of the different nanoparticle sizes. Even it seems that the larger nanoparticle size restructures more. For the carbon dioxide hydrogenation experiment, we see basically no restructuring, and what we can see, if we can see something, it is in the Zanes region, in the electronic region, and we saw some oxidation in our previous experiment, so that makes sense. So counterintuitively, our structure insensitive reaction shows a whole bunch of restructuring going on in the nanoparticle. So if we take a look at this restructuring and we take these two different points in the spectrum and we quantify the surface normalized restructuring that we can detect with our X-ray absorption spectroscopy, we can see that, funnily enough, or interestingly enough, the largest nanoparticle size of the catalyst particle size with the highest activity that we measured restructures the most, or oxidizes the most, or has the most surface normalized changes in the XUS spectrum. But there's very little restructuring going on. And again, for the structure insensitive reaction, a lot more restructuring. And interestingly enough, there's particle size dependent restructuring for a structure insensitive reaction, which was very, very strange. It's strange that something like this would occur for a reaction that shows absolutely no dependence of the turnover frequency with particle size. So we took a better look at the X-ray absorption spectra. So if you do a Fourier transform of an X-ray absorption spectrum, of the K-space of an X-ray absorption spectrum, of the wiggles, let's say, you can get something that's very close to a radial distribution function of the average absorbing atoms next nearest neighbors. Not entirely true if you look at the XOS equation, but let's look at it as a radial distribution function. At which space am I running into my next nearest neighbor, or the second shell next nearest neighbor, which you can see at about 4 angstroms here, and about 2 angstroms you can see the first shell, we call this. So here you see the reduced catalyst, and in green here you can see this ethene flowed catalyst sample. And anything smaller than a metal-metal bond, in our case, where we're flowing only carbon, should in this case be a nickel-carbon bond. Any shorter distance than a nickel-nickel bond is, in our case, a nickel-carbon bond. So it could very well be that the restructuring that we were seeing is being caused by this nickel-carbon bond, by perhaps a very strongly adsorbed nickel-carbon intermediate on the surface of our nanoparticles. So as I said, we did a quick X-ray absorption spectroscopy. We can measure very fast an X-ray absorption spectrum. And we did so, again, pulsing in this case, CO2, hydrogen, CO2, hydrogen. And in this case, ethene, hydrogen, ethene, hydrogen. And just for the record, we also did this with mixtures of CO2 and hydrogen, and ethene and hydrogen, to completely simulate, let's say, catalytic conditions. And the results were the same. But for simplicity, let's look at this ethene hydrogen pulsed experiment. We start in hydrogen, pulse ethene, hydrogen, ethene, hydrogen, and so on. And very interestingly enough, we don't see this feature appearing and going away for CO2 hydrogenation. We do see it for ethene hydrogenation. And this is at 4 angstroms. This is the second coordination shell of our X-ray absorption spectrum, of our average absorbing atom. And that means that there is more and less periodic structuring that is repetitively occurring. So we can see our particle restructuring, disordering, ordering, breathing and relaxing, let's say. And it's reversible. That trend is reversible. It restructures depending on the adsorbate that is exposed. If we then take the difference of, let me explain this a little bit better. We have in our XF's equation a whole bunch of dependencies. One of those dependencies is called the Debye-Waller factor. And the Debye-Waller factor, if all things in the experiment are all other things are equal, we can take this as a measure of the disorder of our nanoparticle. And plotting the derivative of that to time gives us kinetic measurements, gives us a kinetic display of the disordering that's going on inside of the different particles. And again, here, a large, medium, and small nanoparticle were plotted, and we can see different trends in the kinetics of the restructuring that's going on in these different nanoparticles. 3 different things we could observe. Firstly, adsorbate-mediated surface restructuring decreases with smaller particle size. So we can see less restructuring for smaller nanoparticle sizes, interestingly enough. Larger nanoparticles restructure faster. This peak is sharper. And then lastly, there's always a degree of ethene-induced restructuring that's irreversible. So once the peak in the beginning is always the highest. Once this one occurs, this restructuring peak occurs, basically it never goes as high as that again. So there's always some surface restructuring that's irreversible, and this is a very important part. So aside from those X-ray absorption spectra, which is of course a bulk technique, a bulk way to look at all of this, we tried to see if we could see the same effect with a single particle technique. So we verified with in-situ high resolution transmission electron microscopy and saw that these restructuring effects, this expansion of the lattice, was also measured in these conditions. We had a single nickel nanoparticle, reduced it, and then started to flow ethene. And based on a fast Fourier transform of the lattice grains that we saw, we were able to see the same type of expansion. So just a quick recap in trying to build this picture of this new frame of thought. We already knew that we had to take into account step A to B and B to C, and that those may have different active sites with different activity. We now also know that a nanoparticle restructures. So step B or C, or A to B, or B or C time Y might look different than it did in time X. And to fully capture the turnover frequency or the activity of the active site of a nanoparticle, we argue that you should actually take an average of all of the activities of each available site for each reaction step. And that should be weighted by the importance, which could be something like the relative energy barrier of that step and the fractional occurrence of that site. So it's actually quite a bit more complex as it's either an active site or it's not. But with the correct sort of surface titration techniques, with the development of new tools, we can definitely be able to also measure something like this experimentally, hopefully. Going back to this structure insensitivity story for a little bit, we saw that there was a certain amount of surface restructuring that occurred, which was irreversible. And this actually led us to think about restructuring as being the explanation for the observed structure insensitivity. What if, irrespective of the previously exposed surface, when you flow a adsorbent like ethene, which apparently very strongly adsorbs to the surface, strongly enough that it restructures the nanoparticle, what if that actually exposes sites that are all of the same geometry, or all of a much more similar geometry than beforehand? And to test this hypothesis, we did an experiment of a structure sensitive reaction, right? CO2 hydrogenation. We can see that the turnover frequency changes with different catalyst particle size. And then we took those catalysts again. We flowed ethene over the surface, then removed all of that ethene. So we were left with only the irreversibly restructured surface, and then did CO2 hydrogenation, and then saw that this previously structure sensitive reaction became structure insensitive, and still had some adsorption sites available where CO2 could hydrogenate. So actually, rather than having structure insensitivity, it should actually be termed apparent structure insensitivity, because the surface restructuring that occurs most likely causes this empirically observed structure insensitivity effect. If I still have some time left, then I will go to the last part of the talk.
Yeah, we're if you won't, please won't make it too long. Then we have a bit of time for the question and discussion. That would be great, Charlotte.
It's just a few. I think I'll be able to finish it pretty fast. So just to go back to the enzymes, right? We discussed in detail what the active sites of metal nanoparticles look like. How would it look like if we would build an inorganic mimic of that enzyme? This is what we did with polyoxymetallate structures. Just very briefly, this is a Keggin type polyoxymetallate structures where these are tetrahedra of tungsten and oxygen. And this in this work, together with Ronnie Neumann and Dima, the PhD student who worked on this, we came up with a modular way to synthesize these polyoxymetallate catalysts. They came up, I should say, definitely not a synthesis person. In where we could interchange these three metal atoms modularly, and built in this way a mimic for carbon monoxide dehydrogenase catalyst. Again, taking those three metal sites and making them either copper, iron, or nickel, or any combination of those in between, we could see that we got very high turnover frequencies for homogeneous electrocatalysts, reasonably high, 10 to the power 2, much faster than heterogeneous catalysts, generally speaking, and not yet as fast as enzymes. We were able to see that this activity was caused, or the opposite activity, sorry, that we saw, either forward or reverse highly active catalysts for CO2 hydrogenation or CO2 oxidation, could really be explained by the same principles that we were discussing before with heterogeneous catalysis. For iron nickel catalysts, very active for the reverse reaction, we could see an early reaction intermediate. CO2 was very well stabilized, whereas for the copper-3, which was very active for the CO2 reduction reaction, we could see late reaction intermediate. CO was very well stabilized. And that difference in activity brings me together to this whole picture, where I think that we can agree that most of our catalytic activity is caused by electronic descriptors in whichever way we can alter them. There's also quite some dependence on geometry, and then also confinement is a physical parameter that we may separate that really contributes to the active site, particularly in examples like Z-like catalysis. Also, when we're trying to mimic this really high activity of enzymes, confinement becomes a very important feature in trying to design new catalysts with extremely high activity, and we can see this also in this polyoxymetallate example. Right. So the key to designing these types of catalysts, a few metal atoms, most likely, electronically well decided, very specific placement, right? Geometry and confinement, a lot of protein bulk are the keys in order to design these types of catalysts. And this picture to end, Langmuir and Taylor were playing chess, right? We've known now since 100 years that the chess that we should be playing is actually 3D chess. I don't know if any of you know the Big Bang Theory. This is where we got that picture from. The rules are actually much more complicated, and we need to take that into account when we're trying to design catalysts that have the abilities that we need them to overcome the energy crisis, etc. So all of this work was made possible by a lot of people. I want to thank Bert, my previous promoter. I want to thank the Technion, Ronnie, and all of these other collaborators who have made all this possible. And then finally, also, of course, my group. I'm very grateful to these people who all decided to join in the last couple of months, and we're working on some exciting stuff to supplement all of this that you saw today. So with that, I would like to take any questions. And thank you very much for listening.
Okay, great. Thanks a lot for a very interesting talk. Great overview that you were giving, Charlotte.
Thanks so much.
So yeah, if you want to ask a question, please raise your hand, and I can appoint someone that can start with the first question. Yeah, Mariam, please go ahead.
I go with the first question. Thank you so much for the great talk. I really enjoyed. you know, your beautiful slides, science and everything that you really explained in details. So my general question out of curiosity is, have you ever thought about doing the same calculation in different, let's say, environment, especially considering pH, how it does affect on catalytic activity?
So I said this a little bit before to Tom already, but where my group, the people that you see on the slide right now, most of them are working on electric catalysis. So over the past year and a half or so, I've been starting to work on electric catalysis, and this is what we're trying to see. How do these principles that we were able to define and really quite sharply were able to select, how do these translate to electric catalysis? There's at least the addition, for example, of solvation, which is again correlated to electronic effects, but should be taken separately. How do these contribute to overall site activity? So to make a very short answer, no, we haven't done pH calculations yet, but these types of things we're starting to include. Solvation effects, geometry in electric catalysis, pore sizes. Yeah, the picture all becomes also much more complicated once you start.
I bet,
yeah.
Because there are a lot of parameters that you know, we can consider. It's very complicated always, especially when you work with catalysis. And one of the things always in my mind is how pH does affect on even stability of the catalyst, you know, on like, let's say, nanoparticles. And by the time how it does react with the, I mean, just like the surface area and so on. But thank you so much. It was really good time.
Thank you very much.
Okay, thanks, Mariam. Other questions? I was wondering, let me see, it was, I think, slide 29, Charlotte, where you showed this breathing of the particle, so to say. Yeah, I think we just had it right with the lattice distance that was changing.
You wanted this one?
Yeah. I guess when you make the Fourier transform, then you're sure that is constant throughout the particle, or could it even be that there is a slight deviation between the center and looking at close to the outside of the particle?
So this is actually a very very interesting set of questions, and there's lots of different things that are happening actually, which are important to touch upon. So first of all, I was very surprised when you looked at the X-ray absorption spectroscopy that you saw that a larger nanoparticle restructures more. It's quite counterintuitive, and this could be explained. We think that it is explained by grain boundaries. The speed of carbon intercalation in grain boundaries can be up to an order of magnitude faster than over full surfaces or over facets, over exposed facets. So this is one thing that is going on. Second of all, I wasn't able to obtain with enough statistical significance separate values for different parts of the nanoparticle. Here we just took the overall nanoparticle, as actually we would also compare it to the bulk analysis that we did in XAUS. But it's very well possible that there's a difference in a couple of shells, for example, on the surface of the nanoparticle. Of course, what we're doing here is transmission microscopy. So we're taking, you know what, whichever way you want to put it, we're taking the average of the nanoparticle, and that's why also it's so strong to show that this was over, you know, all of the different nanoparticles that we did this with. It was a significant expansion. Yeah.
Okay, great, thanks. Erdem. Oh, you have to unmute.
Yeah. Thank you, Charles, for the very interesting presentation. I would like to ask more on the synthesis part and its effect. once I also involved with the synthesis, especially when we are targeting a particular size range, a narrow particle size distribution, or a particular exposing particular facets. It's very common to use some ligands, capping agents, typically oleoamine or long ligands. And yeah, when we are transitioning into the testing of those catalysts, have you also seen an effect of these agents? Because when we also try to remove those ligands, then the particle shape can change, agglomerations can happen, or when they stay, they also change the activity a bit. So did you have any experience on it?
So my personal preference is not to use colloidal particles or ligand stabilized particles when I'm studying these types of things. So all of these catalysts were either formed by homogeneous deposition precipitation, where really we had, I didn't make these catalysts. We had somebody who was very, very experienced in, well, these specific catalysts are something else, by the way, but the nickel nanoparticles on the silica that you saw, those were homogeneous deposition precipitated. And just by tuning the parameters of that onset the nucleation of both the salt and the support, we saw these different we were able to obtain these different nanoparticle sizes. For other ways to prepare these types of catalysts, I saw also that Andreas is here today, or is in the Zoom. I used spark ablation nanoparticle generation, which is also a way not to have these colloidal nanoparticles. And this worked really excellent here for the silicon nitride membrane that we had, this MEMS reactor. We deposited those nanoparticles via diffusion, so they're not size selected.
Right.
But since it's such it's a technique where we can actually look at single nanoparticles, we were still able to determine the influence of particle size also in this expansion. So there are techniques to avoid colloidal synthesis. I try not to use colloidal nanoparticles for my research. Yeah,
I agree.
Because these ligands, you see that we see that there's so much of a difference between the interaction of different sites, of defect sites with atoms, right? And where would you expect your ligand to remain? Probably in the place that is most active. So.
Yeah, I assume this is a very, very strong technique to study the fundamentals. I always ask the question myself about the upscalability of those, but very, very, very interesting insights. Thank you very much.
Thanks so much.
Okay. Yeah, with that, I'd like to finish now, and thanks, Adam, for the question, the general questioning and discussion, because we've reached 1:30. So people that are interested can perhaps stay around for a bit. Then in a smaller group we can briefly continue the discussion. But for now, I would like to thank Charlotte so much for a great talk. Very, very instructive. So several people also commenting that it was very inspiring, very clear. So excellent. Thanks a lot.
Thanks so much. Thanks for listening.
Yeah.